Today we're going to talk about composites, and I found a few. I'm going to do it a little bit by examples because you probably all heard about composites, and it can be very great sometimes from a mechanical standpoint, but when it comes to manufacturing and overall cost, they are essentially not accessible to a lot of applications. So I'm going to give example of where they are used in large volumes so you have an idea of what you could be using them for. Before I do that, I did want to cover just a little bit more on the metal matrix composites. So I mentioned about brakes for automotive that could be made of aluminum-based metal matrix composites. So you can see here two cases. One is with about 15% alumina and 15% silicon carbide. What you can obtain in terms of a combination of tensile strength and fracture toughness. So it's possible with both fillers to reach a fracture toughness above 20 megapascal square root meter. So it's still a structural material. It can resist cracking. It has some damage tolerant capacity. And obviously, as you can see about the overage and the underage, so we have an effect here as to whether the aluminum has big precipitates or small precipitates, because the small precipitates, they give you more hardening, they give you more energy absorption at the crack tip. So this is sort of tying back to some concepts we talked about for fracture toughness. They are in use, and I actually had them on my car once, although one of the issues, one side was ceramics, and I think the pad weren't, or the opposite, and then you don't necessarily increase your duration of service between times going to the garage. But nowadays it looks like they change both parts at pretty much at the same time, so you can increase your life. I'm giving this to you as just a little bit throwing the idea here about different types of composite you can have for optimizing the strength for a certain weight. So you're looking at the specific strength here, and you have the polymer-based composite, which is what we're going to talk about today, and you have the metal matrix composite that would go to somewhat higher temperature. You have a carbon and graphite based systems that will essentially give to you more strength. Sometimes strength comes with brittleness, but when we were talking about super alloys, we had those charts that were extending beyond for ceramic composites, essentially, that have some fracture toughness because you have fibers that are, if you crack the matrix, you still have the fibers to bridge the crack. And that's one idea that for you to keep in mind. So when we're looking at these carbon-carbon composites here at very high temperature, you still need you need thermal resistance. There are a lot of oxidation requirement that you need to be able to meet, either with a coating or with your base material. But that's pretty much how you could go beyond what the metal could do, which is more of the order of 12 to 1400 degrees centigrade. So here we're really talking about these composite materials. So as far as applications where we're more into ambient temperature, you can reinforce a polymer, an epoxy, for example, or a polyester, so thermoset resins, with glass. And glass is essentially a relatively low-cost material, depending on which shape you want it. It doesn't give you the stiffness that the graphite fibers give you. So we talked in aerospace about graphite composites quite a bit, and one advantage as opposed to glass is not a little bit on the strength, because here the dotted line is not the composite. So the composite ends with this dot here with a vertical bar. So between a glass based composite, glass reinforced composite, and a graphite reinforced composite, you have a slight difference in specific strength, but you really have a large difference in elasticity, in stiffness. So that's essentially the type of materials that we're talking about today. Things that will essentially allow you to be lighter weight at the cost of having to put the resin and the reinforcement together in a neat assembly. When I talked about the specific strength, we can also talk about this as a creep or fatigue resistance. So if you remember, for metals, we had our SN curve, which we could stress, and we can put a number of cycle or time here, and we have a curve that looks like this, and it somewhat stabilizes, and we have, or if it's fatigue, it's around 10 to the 7 here, that it's starting to slow down in terms of capacity. So you reach a certain capacity. If you're looking at a composite and say this is one cycle here, so say this is the tensile strength or the yield strength. If you're looking at a composite, with respect to the tensile strength, the curve is going to be higher. And there are a number of reasons for that. One of them is the value of this resistance here is largely governed by the fibers. The fiber prevent very small cracks or voids to grow beyond a certain size because they bridge them on the first place. So if we have short fibers in a resin that we mold, for example, you can prevent the formation of cracks that will lead to a fracture at a higher proportion here of where you started for your ultimate tensile strength. So what I should do here is just do a ratio presentation, and that's what this is showing here. So you have a static tensile strength of, say, about 900 megapascal, and if you go at 10 to the 7 cycle, you're still above, or around above 700. So it's a higher ratio of the fatigue limit over the tensile strength, and it's not unusual across the board with composites when your reinforcement is effective in bridging cracks. The sequence of events that lead to the composite to fail, either in creep or in fatigue, it first involves the separation between your resin and the fibers, and that's what we see here as debonding. So if I have a crack, a slight pre-existing crack in the material, and I have, say, a fiber right here, and I'll make it discontinuous for now. So I have those two fibers that are holding. I'll have a lot of shear stress on that interface right here between the void space and my first fiber. So I'll start to debond and eventually keep moving up, and I can eventually free up this whole interface. So at this point, the fiber is separated from my resin. Now, if the fiber is longer, maybe I'm only going to get to a certain height, and it will still be bridging. And that's part of the decisions between using one or the other, or using continuous fibers. But in all the events, it's very typical to have some debonding to happen first, and then if this is a continuous fiber, I'm going to draw it continuing essentially. I can't debond it separate completely, but if I debond it over enough, then it can buckle and break in tension compression in cyclic loading. So this idea of making a separation between the reinforcement and the fiber is really the first thing to happen. Then you crack, and I have an image here where eventually the crack will have to go between fibers. So if they're not continuous, that's a preferential site. But you can see how jagged the crack is in this case. This was a bending experiment. So it started cracking here. It went through about half of the thickness and then started to transition in shear. The nominal stress, tension stress was going down as you keep going through the material. And eventually you have more of a delamination fracture. So it didn't go really through the thickness. You note that the reinforcement in terms of strength and stiffness will vary greatly with orientation. So if you have a piece of fuselage for an aircraft, and that's actually one example to give to you about making these decisions. So there are a few aircrafts that have the whole superstructure made of composites, and that if it's been in production for more than 20 years, it's known to at least one model is known to have some stability issues and get into a spin mode, and without going into the details of aerodynamics, which maybe some of you could, but the idea of reducing the weight of the overall aircraft by more than a certain amount clearly can affect other things like dynamic stability. So there's always a limit on how much you can move before you design before getting into other problems. And it appears to be the case with the composites. We say as a joke that you could put some lead shots at the end of the wings to stabilize it, and maybe still have some weight benefit, but it's just going completely composite was very expensive, but it also led to other issues that they were not expecting in the first place. One of the issues is deciding between strength and stiffness. What is your governing criteria? Because so here I'm plotting the change in the elastic constant. If we're talking about a fuselage, it won't be rare, and I'll draw it as a cylinder for simplicity. Well, we have to decide if it's a small aircraft or if it's a jet. If we take a jet, essentially it's pressurized on the inside when you are at cruising altitude, and so you have a lot of hoop stresses. So your stress in this direction is high from pressurization. You also have stresses in this direction from the bending of the overall aircraft. There are stiffeners, but you do use the skin as a stiffener with the engine in the middle and all of this. So you need stiffness in both directions if you don't want to be fluctuating too much and you want strength. So if you build a composite for this application, you may say, well, I'd like it to be twice as strong in a hoop direction than in the longitudinal direction, and you can do that. There's nothing that prevents you from orienting the fibers the way you want, especially if it's a series of overlay. And that's what I'm showing here to you on the photograph. There's always a risk in terms of mostly from an analysis, but also from a behavior standpoint, when you stack different layers with different orientations. So this one here would essentially still be about, well, maybe a little stronger in this direction here, especially if you have bending loads. So you have to determine if for one condition, this one, the longitudinal tension is likely to be through the thickness unless you're in the buckling. So if you're looking into the compression here, you can have some bending load as well. So you have to make a decision, which layer are you going to try to optimize for the skin? And you can't do it any way you want. I'll explain that right here. If I take essentially a strip of that composite and it's oriented with fibers sticking in and out here, and then on the other side here the fibers are running the other way. So I have fibers going this way and then I have fibers going the other way. If I pull on this material, it's actually going to bend. So when they use the term theory of laminates, the idea there is you want to try to avoid generating bending deformation by just an in-plane tension, and vice versa. If you bend something, you don't want it to be loaded in the other direction as well. So it's a combination of this concept, the concept that your stress would be different in one direction than in the other, and some practical issues about, you know, strength and compression as opposed to strength and tension, that will help you determine which kind of composite you can use for a certain application. Obviously, you can get more specific orientation. You can decide to go at 30 degrees, 45 degrees. There's a lot you can do with unidirectional fibers. There's less you can do with a woven fabric like here, and this is typical of fiberglass, where you essentially have a mat that you impregnate and put over a form. It's easier to do. You can use, in this case, we can see the size of the fibers are different in one direction than in the other. So it means for our application, if we say we have more stress here, we have to make sure that the long fibers are going around the circumference, the bigger diameter one. So you can probably see already that in actually designing and making the composite, there are a lot more steps and decisions, and, you know, also risk for errors if you don't put the mat in the right orientation, for example. So it's all established technology. It's used for small aircrafts. It's used for jets also, for the tails, for example. The way we do some of these composites, this is not all inclusive, but it gives some idea about the different ways to make a composite. So I want to introduce it. One is you blend the resin with a suspension of fibers, and then you can mold it. So it's typical for nylon, for example. If you have nylon-based parts, polypropylene, you can do it this way. Some polyethylene have reinforcement. Sometimes you put fibers or particles to increase your stiffness at low cost, because some of the small particles that you can put in the resin here can be very low cost. You can put sand and reduce the amount of polymer you're going to need to make a part, but it's generally reducing your mechanical properties. The squeeze flow here is slightly different, because now you have the fibers laid out on the first place, and you essentially have the layers stacking up together. So I could take a sheet of a polymer and put my fibers on top, put another sheet of polymer, put another fibers, and then heat everything up and blended together to create my bonds, because the bonds between glass or carbon and the resin is really important for all those fracture characteristics that we talked about. If you impregnate it, that's another process that we're going to talk about. So in this case, you have all your network of reinforcement in place in a mold or on a form, and then you push the resin through it to make the composite. It's generally more expensive, but obviously you can generate more the layout that you want with this process than with the others. Now, we're going through a few examples. Pipes. High pressure pipes, very high quality pipes for, say, fire suppression systems in nuclear plants or industrial plants have this system where you start with a plastic core and you start winding the fibers around it. And it's typical, you can see it on the yellow pipe here, to have a wrapping at a 30-degree angle, plus and minus, and you go around and essentially make your pipe more resistant to the pressure. One advantage of doing this process where you start with a core is you can preload your fibers. So as you put them on, you stretch them so they are in tension and your plastic is in compression. So it has that advantage of creating residual compression in the polymer that's around it. So when we're thinking about forming these voids here in the resin as being a problem, if you put a nominal compression in that resin, you're going to reduce, if not eliminate, that risk. It's used also, this process with concrete cylinders. For the same reason. You start with a core and you wrap steel around it with a lot of preload in it. Takes the whole concrete cylinder, put it in compression, and then you just cover these wires for corrosion protection, and that's the end of your process. It's essentially the same idea of wrapping and including a preload. Now they make very complex shapes, and one of the reasons for these composites is some of them will be very resistant to chemicals. They will be more resistant than the equivalent metal. They're also very lightweight. But they cost a lot of money. If you look at some of these complex fittings, they cost a lot of money. And joining them is very difficult, because if I have two pieces of composite, I try to join them, I won't be able to connect the reinforcement in one with the reinforcement in the other, the pre-stress in one with the pre-stress in the other. And that's why this bell and spigot system for pipes anyway and fittings is very attractive. It doesn't require any real bonding between the two sections. It really relies on a gasket here to hold the pressure between them. So typically when you do that, you have to reinforce the bell here, and you can see it's thicker. But it allows you to make pipe connections that also can take some stretch. You can have some slip between the O-ring gasket here and the bell during installation or in service. The concept of this winding is mostly for large volume production. You do need equipment to be able to do it consistently. So it's not something that if I want to make 5 of something that I can do easily, as opposed to metals. If I want to make the same fitting out of stainless steel, I go and buy some plates, bend them, and weld them together, and I'll be done with it. If I wanted to do it out of that composite, I'll have to arrive to a way of wrapping my fiber around these complex joints and still develop the strength. This is a lower end application. These underground storage tanks are used now in more than 50% of the gas stations. They're all made of composite. The other 50% is still made out of steel. What the cost, the equivalent cost, I did some more research to stay up to date with it for the purpose of today, and they say the equivalent cost is comparable nowadays between buying, for the life you can get out of it, between buying a steel tank or a composite tank. And it makes sense if 50% of the market is converted and other people are still buying steel tanks. It's just not that clear. If you do the composite tank, you have to spend more money. Yes, Professor Eager?
But that's a slight apples and oranges comparison. The steel tank is double wall, so it's 2 tanks.
Okay.
Right?
Professor Eager is pointing out that there's a difference in pipe thickness between them, and it's true that essentially the regulation allows you to use less material in the case of composite because you don't have to take into account interior corrosion or exterior corrosion. And with the steel tank, you can generally put anodes around it to minimize your external corrosion, but you're still going to have a risk. And going back to the comparison, steel and composite, what I wanted to address was the difference in how you backfill around the pipe, the tank. So with the steel tank, it's very stiff and strong, and it's not going to be subjected to creep over time. And therefore, you don't have to be as careful in how you put the soil back together around the tank. With plastic and composites in general, you have to be careful with your backfill. It's the case with these composite tanks. It's also the case with some storm chambers that you can put underground to take the water from the roof in large buildings and have it absorbed by the soil under the parking lot, for example. So you have these structures that are built to go over a very large area that are essentially air gaps under the pavement, and it'll be used and filled with storm water. In both cases, when you're dealing with a composite or a plastic, you have to think about, okay, if I overload them on day one because I don't put it back correctly, and not putting it back correctly is if you don't have good support soil that goes under, the spring line of this pipe. It will essentially dig its way into the soil and becomes more of an oval over time. It's not a problem you have to worry about with steel, really, but it's really true for composites that it's one of the requirements, and it will affect your performance. So it's a field installation aspect. But as far as how the tank is made, which yep.
You see those white straps across there?
Yes.
Assuming that's an installation, something that always surprised me is whether it's a steel tank or a fiberglass tank, when they're not full of liquid, they will float out of the ground unless you strap them down. You actually have to anchor them to the ground. So you might have a concrete pad with bolts sticking up, studs sticking up, and then you put a strap over it. In this case, that white strap that you see there, or a series of white straps, keeping it from floating out of the ground. Okay. So
that's a bit like we were talking about the aircraft, right? you should put some lead shots in it. Okay, let's talk a little bit more about how it's made, and then a little bit more about the advantages and inconvenience. So, a relatively not expensive way to make it is you start with a female mold, so you have all around with these reinforcement ribs. So you see the ribs here, and the purpose of them is to prevent the pipe here from collapsing this way. So it provides this stiffness. It's not for pressure, there won't be any pressure, so it's to resist gravity. You build it from the outside, so from the inside, well, You build the outside surface first, and you spray from the inside. So say I start this way, I make the rib, and then I come with a mat that will essentially cover that rib, so I don't have to spend the money spraying this whole rib with polymer. I make my way through, and then they have an interlayer, because this is a double wall system for safety, which essentially is supposed to be porous enough to communicate the leak all the way down into the lower point in the pipe. And then you have the inner layer that's just a flat. So this is built without moving anything, without making any joints. It's all happening one after the other when the resin is still hot or soft, and everything is bounded together. It's essentially something to think about if you're going to make a composite. You want to avoid cold joints, because we talked about the cold joints, the fact that you're not sharing the reinforcement. Here, you're essentially sharing more or less the resin and the reinforcement, because I didn't say, but it's a sprayed system where you spray short fibers with resin. So you keep building it up by spraying from the inside onto the mold, and it's essentially a one batch process. It all happens at the same time. And we talked about essentially that being more expensive material, definitely per weight, and for the application you spend more money on making that composite wall than you'll make in making the steel tank. But you don't need sacrificial anodes. Your thickness somehow can be less based on the requirements. You can resist the gasoline more or less, and that can be debated, because the resins used on those systems, I had to study them once or twice, and they are sensitive to solvents, essentially. If you take a polyester resin and you throw alcohol through it over an extended period of time, it becomes softer. To the point where if you have permeation through the thickness, you could start seeing blisters. You can have a lot of issues. So thinking of composite as being completely corrosion resistant is incorrect. They are affected as well. The honeycomb structures, a lot of you probably heard of it before. Essentially, you have a low density core, and you have those faceplate, and the general term I use for it is a sandwich composite. You put some, it's not the meat, you actually put some filler in the middle, and then you have your real surface, your working surface on the edges. The joining of it, and you can see the system here with taper joint, is typically a problem, because if you try to use fastener, or you can't really weld it, but if you try to do anything other than tapering it here, you're at risk of crushing it. And I remember when I worked at Bombardier Aerospace, they were talking about selecting the honeycomb to resist the high heel shoes of the passengers. So you use the honeycomb as a floor on small aircrafts anyway. And if you think of it from a gross load perspective, there are no issues. But if you think about a localized load, that's where you can have that crushing taking place. So it can be the case also for cars. There are cars that will be built on a type of a sandwich construction, and they are at risk for the same thing. It's easier to dent it on one spot. It's good for overall stiffness, but for touching it on one spot, it's less resistant. This is one case of a sandwich structure that puts together aluminum and an epoxy glass reinforced composite. So the intention was for fuselage applications. And one aspect you can see is how you can reduce the crack propagation rate. So these plots, we haven't dealt with them too much, but you're looking at a logarithmic crack growth rate here. So there's a factor of 10 in rate between each line, and then we're looking at a stress intensity. So how much load is on our sample. So if you get to relatively high load, let's say we take 20 here, we have about two-fold difference, so 100 times difference in rate between having or not having these fibers to bridge an existing crack. Now, in this case, we have layers that are completely aluminum. So you crack the aluminum all the way through the thickness of that layer, and it's the fibers in the composite layout. So if we go back here, I crack the aluminum, and then it's the fibers in the other layer that's holding it together. So it's a very different way of thinking about a composite. The disadvantage of a system like this, well, one of them is how are you going to ensure that the different layers, they have different thickness, stiffness. How are you going to ensure that they will resist moisture penetration and essentially maintaining the bond between the different layers? And that's one thing that by field evaluation, prototyping, they had a lot of issues with maintaining the bond between the aluminum and the epoxy on the long run. I want to introduce these different orthopedics component. First, thinking about composites. With composites, we talked about being able to modify the properties in the different direction, and you could essentially make something that'd be good to go into the body, but then how are you going to connect it? So it turns out that metals will be bonding better to the cement and sometimes the bones in the body than the composite. So on the first place, you have that issue. You'd like to use something that, say, has the right stiffness, because you can tailor it with the composite, but then you can't connect it together. So you have a problem. And it's the extreme example that I want to briefly introduce, that you can't think of changing one component of a system for a composite. Like if we're talking about the fuselage, and we would like to essentially use a sandwich structure, then how are we going to make the joints? We'll have to arrive to some special lap joints with a tapering. It will be good in bending. That's what sandwich structures are for. But if you try to make the joint and try to clamp it together, that's where you have your crush zone. So joining of composites, or in material selection in general, is very, very important. I think we've covered these key items I wanted to introduce for composite: the high specific strength, the good fatigue limit and yield strength ratio, high damage tolerance because you can bridge the cracks, very difficult to join. We talked about mostly the humidity resistance of an adhered layer, but also for the tanks I mentioned about solvents being a problem for the composites. UV light is a problem for those filament wound pipes. So they are essentially designed for underground. And if you try to use them above ground, you have the UV light changing the stiffness, the level of cross-linking into your matrix, and it's going to change the properties over time. It will degrade on you. Oxidation is something that's very common with polyethylene. You can have degradation of most plastic and composites if you expose them to sufficient severe environment. So I want to put some pluses here on our summary chart for composite as strength, toughness, fatigue, and a minus. I should make it a big minus here for joining. It's not that it can't be done, but you have to think about it very seriously. The last example I want to talk about, now we really covered these categories of materials, and I have this wind turbine that I worked on a while ago, so I'm only going to describe it in a general sense, but the idea was to have a shroud, so to have an exterior layer. You have the blades here. If you've seen them nearby, most of the time it's just the blades spinning around. Their idea was to put a shroud, and it still is, to put a shroud to funnel the airflow and therefore increase the power generated by a certain length of blade. If we look at it here, there's a little bypass zone. There's these very specially designed shape to create a vortex effect behind the turbine that essentially drags more air into it. So we essentially have an effect of the air blowing through it as a source of power, but the effect of suction of pulling the air through it, that's a little bit the opposite of a turbine engine, where you have the compression happening first to push it in. Here we're really pulling it just by the wind dynamic design. Now, it's a big structure. Say, well, these are actually smaller. It's a marketing image, but it was about 80 feet across for diameter. So about 4 pickup trucks. What? Yeah, I know. Yeah, it is what it is. Maybe you would put it the 80 as this outer layer here, but it's still pretty big. The idea with this is now becomes cost. All the wind turbines from day one is all a question of investment costs. How much money does it take to go put one out, build the foundation, put the post up, and put it all up and running? So they wanted to minimize that, but when you're talking about such a structure, it can't be that cheap. It will cost money to build something that has this level of complexity, that needs to be able to resist wind. It needs to, in any condition, you can have a hurricane, you still don't want the whole thing to come to the ground. And there's no way to, the only way to make this hurricane proof in terms of retractable would be to use a flexible skin. If you use a skin like some of these signs that are down in southern Texas, the sign will break before the post comes out and things like that. So you could have that concept in place here, but I don't think you want to unless it's really a fabric. If you had a fabric making up that skin, you could have it flexible, but fabrics are also expensive to make and not necessarily a long-term performance item. So if we look at our choices of material, well, we can think of aluminum because that's what we use for aircrafts if we make a similar size structure. But it's expensive. Say you take a bulk value of $2 per pound, then you start having to think about how you're going to join it together to make such a complex structure. The composite, if you look at it from a raw material perspective, just the resin and the glass, it wouldn't be impossible. But when you start to think about how you're going to make the molds to generate a range of sizes and a variable level of production, it's a very, very serious enterprise. And you still have to worry about the UV resistance, the moisture penetration, because this is exposed out there and you're thinking about very long term. So from a cost perspective, steel was the best. It's unfortunate. The advantage with steel is you can put some stiffeners inside your skin and just weld it on to essentially make the whole if we're looking at this shape here, make this whole shape resistant to buckling. So the welding was a big advantage. As far as corrosion resistance, well, it will stain eventually, and that was a big problem for the client. They want something that looked white and neat, you know, all through the prototyping, and it's very hard, especially if you're going to make some, if you're going to put different segments together in the field. This was going to be built in 3 pieces across the circumference and then assembled together to make it, to put it up on the structure. So I think we can all agree that you can dream about anything. You can think about, and it's good to know these different material options, the advantages, the disadvantages, but when it comes down to the bottom line, a lot of times the options are just going down by themselves. So that's why the way I try to teach this class is give you some background in each area so you can start your own elimination process when you think about a certain application. It's very rare that you can eliminate, you can look at one variable and pick a material based on that. You're going to end up having to look at a number of issues, and we have some on our summary chart, and then there'll be one that just puts one material out completely, and then you have to move to the next one. We talked about material selection, but we talked about a lot of things in these past 10 lectures, and I'm happy if there's something you'd like to elaborate on, if you have questions at any point in time now in the future, I'm happy to help you make any progress with your own projects. For material selection, if you remember these different aspects of manufacturing, we talked about heat treatment. We talked about all sorts of different properties, and they are related together. If you cast something, it's easier to do sometimes, but then you have some disadvantages in terms of property. We have the ratio analysis diagram. Last lecture, or the one before, when we talk about superalloy or titanium, I had this cost analysis. Actually, there's a whole class on cost optimization for material selection. But the idea still is you have to decide what is the limiting factor. There are parameters you just can't live with. If it's too expensive, it's too expensive. You just don't consider it. And then you have these, when you're left with, say, 3 or 4 variables, you can put a certain weight on each of them. And we did that in the class. We looked at tension, compression, and manufacturing as being 3 aspects that we're trying to overall make a decision on. And we had, in that case, the titanium, it was 100%, and we had steel, high-strength steel at 85%. That's not very different when you talk about an overall strength perspective to be 15% between what you think you should use and what your analysis tells you. So it means that you may want to refine it a step further and maybe make it out of steel. Because there's always a limit to the accuracy of your analysis. So it's good to take about all the variables, make the easy elimination, and then work more tightly with what you're left with for making a decision. That's what I have. I appreciate you being here today. If you want to go for lunch, we can go for lunch, because I did not bring the muffin that I promised last Thursday or Friday.